Hi, I'm Farhana. Thank you for joining me for this lesson on 3D trigonometry. Specifically, we're going to be focusing on using compound and double angle formulae in 3D trig problems. Before we begin, let's look at the concept map to see where we are in the syllabus. Okay, so far we focused on solving non-right angle triangles using the sine rule, the area rule, and the cos rule. We've already done proofs and applications. We've started off with 3D problems, and now we will focus on using compound and double angle formulae. Can you remember what your formulae look like? Let's just revise. So the compound angle formulae, there were 4 that we've learned. So cos of alpha plus beta becomes cos of alpha, cos of beta, minus sine of alpha, sine of beta. And when you have a negative value, it's the same, except the sign becomes a positive. And for the sine rule, for the sine one, we have sine of alpha plus beta becomes sine alpha cos beta, and the sign remains the same, so it's plus cos alpha sine beta. And the other version is, if you have a negative here, you'll have a negative here, and sine of alpha minus beta becomes sine of alpha cos beta minus cos of alpha sine of beta. The next formula we do is a double angle formula, and they're quite easy to remember. So sine of 2 alpha is equal to 2 sine alpha cos alpha. And the cos 2 alpha, for the double angle, you have 3 different versions. The first version is this with cos squared alpha minus sine squared alpha, or 2 cos squared alpha minus 1. And the final one, the final version, is 1 minus 2 sine squared alpha. Okay, can you remember which rule to use when? We've done this in the previous lessons. Let's do a quick recap. Okay, so again, if the triangle is right angled and if it involves angles, we're going to use trig rules, trig ratios, sine, cos, and tan. And if it only involves using sides, then we're going to use theorem of Pythagoras. So if it's angles, we're going to end up using SOHCAHTOA, and if there's no angles, we end up using Pythagoras. That's for right angle triangles. If the triangle is not right angle triangle, we're going to look to see if there's a matching pair of angles and sides. If we've got one full pair, that means an angle and its matching side, then we can use the sine rule. And if we don't have a matching pair of angles and side, then we have to use the cos rule. And again, remember, sine rule is used when we have angle, angle, side, or side, side, angle. And cos rule when we have side, angle, side, but you have to have the included angle, or we can find an angle if we've given 3 sides of a triangle. Right, so let's look at our first example. They gave us A, B, and C are 3 points in the same horizontal plane. DA is a vertical cliff. So, and we have the angle of elevation from B to A to the top of the cliff is theta. So they're talking about this angle here. The angle of elevation from the horizontal upwards to D is theta. And they've given us that ABC and ACB are both alpha. So this angle and this angle are both alpha. Okay, the distance between B and C is k meters, and they tell us to prove that AD is equal to k tan theta over 2 cos alpha. Now, again, the easiest thing is go and look at your triangles. As it stands, we look like we're only dealing with the 3 triangles. The 2 vertical triangles, the 2 triangles in the vertical planes, triangle A, B, and D, which is right angled at A, okay? In fact, we don't have any information about this triangle as it stands. We're probably not going to use it. So we have this triangle that's right angled, okay? And then we have the triangle BAC on the ground. And if you notice this triangle, we already have 2 angles. Okay, so we've got 2 angles. We've got one side, but we don't have a matching pair of sides, which means at the moment we cannot use cos rule or sine rule. But because we have 2 angles, we know it's pretty simple to calculate that angle. And once we calculate that angle, and that angle we know will be 180 minus alpha minus that alpha that's sitting at both bases, at the base of that triangle. So in other words, we will have one pair of matching angles and side. Then we can use the sine rule to solve that triangle. Okay, so they want us to actually find AD. So we're going to start off by looking at AD. So AD belongs to this triangle here. Okay? But in this triangle, we only have one piece of information. So we're definitely missing a second piece of information. But if I can find AB, okay, using this triangle here, BAC, the bottom triangle, the horizontal triangle, that means then I can find AB, and once I find AB, then I've got AB and theta, then I could find the side, I could rewrite AD in terms of theta and alpha and k. So we have a strategy. Let's start putting that into action. Okay, so in triangle ABD, we're going to start off with here. So in this triangle that's right angled here, we've got theta and we want to rewrite AD. So AD is the opposite side, okay, over, we're going to find AB. So in other words, tan of theta is equal to AD over AB. Okay, we're going to rearrange that quickly, and when we rearrange that, we multiply through, and we're going to end up with AD is equal to AB times tan of theta. Now remember, we're going to leave this for a bit because we know we want to find AD. We're going to see if we can now find AB. So again, remember when we came to this triangle, we said AB belongs to this triangle here. And we've got the opposite side. And remember we said we can find another matching pair, another full pair. So let's do that. Okay, so in triangle ABC, we have BAC is equal to 180 minus alpha. And so BAC is equal to 180 degrees minus 2 alpha. Okay, so now we're going to use the sine rule. So again, remember, because we want to find, we're looking for AB. So we're going to start off with AB using the sine rule. So AB and the angle across it is alpha. So AB over sine of alpha must equal to, now because they've given us k, we're going to use k, and the side across k, the angle across k is this one, the one that we calculated earlier. So we're going to put that into our equation. So 180 minus 2 alpha. So let's see what we've done again. We were looking to find AB because we wanted to find AB to substitute into here. So we said AB over sine of the angle across it, alpha, is equal to, we used this matching side that we had here, A and K, angle A and the side K, so it was K over the side of the sine of 180 minus 2 alpha. Okay, now we need to do a bit of algebra. Okay, sorry about that. Okay, we need to do a bit of algebra before we do anything else. Okay, so now let's begin by first multiplying through by sine of alpha. So we're going to multiply through by sine of alpha there. And let me just grab my pen. Okay, so we're going to multiply both sides. Oh, sorry about that. Okay, we're going to multiply both sides by sine of alpha. And there we go. We've multiplied both sides by sine of alpha. Now, this again becomes a reduction. This is again second quadrant. And sine in the second quadrant, we know we can simplify sine of 180 minus 2 alpha. Okay, so it's 2 alpha. And remember, because this is second quadrant, sine is positive, so it's just going to equal to sine of 2 alpha. Okay, so this whole expression is just going to become sine of 2 alpha. And okay, so now we have an expression for AB, and AB is equal to k sine alpha over sine 2 of theta. Now remember, we started off where we wanted to substitute AB to find AD. So let's go back to where we started off. We said AD was equal to AB tan theta at the beginning, and now we've just proved that AB is equal to k sine alpha over 2 theta. So what I'm going to do is I'm going to put this in place of AB there. Okay, and there we go. I've put that in place of AB there. Now I just need a bit of algebra to figure out what's happening. And there's one more thing you'll notice here, that we've got a sine of 2 theta. And we know from our double angle formulas, 2 alpha. What must be sine of 2 alpha? It will become 2 sine alpha cos alpha. So we're going to change that denominator to be 2 sine alpha cos alpha, like that. And this 10, we've just taken it to the top to multiply it. And so we've got k times sine of alpha, tan of theta, over 2 sine alpha cos alpha. Remember, we got this from, we've changed that. We've changed the sine of 2 alpha into 2 sine alpha cos alpha. Now that will cancel out. And what are we left with? K tan theta over 2 cos alpha. And that's exactly what they asked us to find. Okay, it's time for an ad break. Please join us just after this. Welcome back. Before the break, we were looking at 3D problems and using compound and double angle formulas to help us solve 3D problems. Let's continue. So in this example, we've got a hot air balloon which is directly above a point B. On the ground, Amy and Dave are standing at C and D respectively. Actually, this is supposed to be A. I'm sorry about that. Okay, are standing at A and D respectively. Should I clean it up rather? Stupid mistakes. In this example, a hot air balloon H is directly above a point B on the ground. Amy and Dave stand at A and D respectively, holding the 2 guy ropes, AH and AD in place. The distance between A and D is k meters. AD equals to 2x, HAB, which is the angle of elevation, is x, and we have that ABD is 90 minus x. Show that AB is equal to 2k sine of x. Okay, so let's just double check. ADB is this angle here, and this angle here, ADB is this angle here, and this angle here is 2x. HAB is x, so this angle here is x. It's the angle of elevation from A to H, and they've given us that ABD is 90 minus x, so we're talking about that angle. They want us to show them that AB is equal to 2k sine of x. Okay, so we need to find something. We need to find AB in terms of k and x. So we start off by saying that in triangle ABD, we know that AB, oh, sorry, James. Maybe I should have talked about this a bit more. Just give me a second, sorry. I haven't discussed this. Okay, so they want us to find something about AB. Now, AB belongs to both triangles, this right angle triangle and this one ABD, the horizontal triangle. Obviously, we don't have enough information in the right angle triangle because we only have x. So we can't use the triangle. We're probably going to use triangle ABD in order to find AB. So let's check what we have. We're looking for that. We've got the angle across it. And if we look here, we've got a full pair of angles and its matching sides. So we've got this angle 90 minus x, as well as the side across it. We have this angle, and we're looking for AB, which means we can easily use the sine rule. So that's where we'll start. Okay, so in triangle ADB, using the sine rule, AB over the angle across it, so it's sine of 2x, will equal to, now remember we're going to use this matching pair, so we're going to start off with k over sine of 90 minus x. Okay, and already you're going to notice that this 2x is probably going to change 2x into what? We're going to use our double angle formula at some point, and we're probably going to end up changing this into 2 sine x cos x. So just keep that in mind. We're going to be using that somewhere. Okay, so first we'll multiply throughout by, oh, we could have changed it in this step. Sorry, I've changed it in this step already. So we've changed it here. And now we're going to multiply throughout by 2 sine x, just to clean up some of the algebra. And so when we multiply that into the numerator. Now we just clean up and cancel out the 2 cos x. And we're left with AB is equal to k times 2 sine x. And rearranging that slightly, we got AB is equal to 2 times k times sine of x. And that's exactly what they asked us to find. Okay, there's another part to the question where they tell us, hence, show that the length of rope AH is equal to 2k tan x. So remember, we found AB equal to that already. So we've got some expression for AB, which means we kind of have this side here. And they want us to find this side here. So, and we have angle x here. So we have the adjacent, and they want us to find the hypotenuse. So because we're dealing with adjacent and hypotenuse, we're talking about cos. So we're going to, because this is a right angle triangle, we don't need to use any fancy trigonometry. We just got to use the SOHCAHTOA. So we can use cos in this case. So ABH, in triangle ABH, cos of x is equal to adjacent. So it's going to equal to AB over your hypotenuse, which is our AH. Now we're going to just rearrange this to make AH the subject of the formula. So AH is equal to AB over cos of x. But now I can substitute this for AB there. So let's do that quickly. Okay, so 2k sine x goes in my numerator. And what did they want us to prove? They want us to prove AH is equal to 2k times tan of x. And I know that this gives me what? Sine x over tan x. We know that tan of x is equal to sine of x over cos of x. So, in other words, we've proved exactly what they want, because now we've got that 2k tan x is equal to AH. Okay, the third part of this question, it tells us, they're giving us now values to substitute. They tell us k is 40, x is 23, HD is equal to 31,8 meters. Calculate theta, the angle between the two ropes. So let's see what they've given us. They've given us, now we know that k is equal to 40 meters. X is equal to 23 degrees. Okay? And they've given us that HD is equal to 31,8 meters. Now remember, they want us to calculate theta. So we're talking about this inclined plane here. With the triangle we're dealing with now is we're talking about this triangle here. Okay? And in this triangle, we have theta. So in the triangle HAD, we have theta. We've got k is equal to 40. Okay? And we have this side here, 31,8. But remember, earlier we did find an expression for AH. Okay? So because we kind of have an expression for AH, we can substitute into that. So let's do that. AH is equal to 2k tan x is what we found in B. So now I'm going to substitute this 40 in for k, and for x I'm going to substitute 23. So we're going to end up with 2 times 40 times tan of 23 degrees. So now we're going to find our value for AH. So now we have that this side here is equal to 33,95 meters. Okay. Now let's go back to our thing. Remember, we were looking for theta. Because we're looking for theta, we're going to see what we have. We've got the side across it, we've got that side, and we've got that side. So we actually have 3 sides, and we're looking for an angle. And we know anytime we have 3 sides and we're looking for an angle, we're going to use cos rule. And specifically, we're going to use cos rule where we're going to start off with 40 squared on the left-hand side. So let's see how we're going to do that. We're going to say in triangle HAD, AD squared is equal to, so AD squared will equal to AH squared plus HD squared AH, HD, and remember, because we started off with AD, we're going to end with the angle across from it, and the angle across from AD squared is theta. Now we're going to rearrange this because remember, we are looking for cos of theta. So we're going to make cos of theta the subject of the formula. So it will be AH squared plus HD squared minus AD squared divided by 2AH HD. Okay, we've done this conversion lots of times. Now we've got to go and substitute into the equation. So let's go and substitute into the equation. That's where we were at, and remember we had calculated, we should have this in the memory of our calculator. We calculated AH earlier. So we're going to substitute that in. So we're going to say AH squared plus HD squared, and remember HD is 31,8 minus 40 squared equals to 2 times 33,9579 times 31,8. And remember again, because we're finding cos of theta, when we're doing our calculator work, we got to use shift cos when we're finding the angle. Okay, so basically we're going to end up with cos of theta equals to this expression here, and we're going to find theta from there, and we're going to end up with theta roughly equal to 74,85 once we've rounded off to 2 decimal places. Okay, it's time for a quick ad break. See you after this. Hi, welcome back. Before the ad break, we were looking at using compound angles and double angles to solve 3D problems. Let's continue with another example. Okay, in this diagram, AB is the height of a vertical tower. C and D are 2 points in the same horizontal plane as the foot of the tower B. From point C, the angle of elevation to the top of the tower is X. BCD is equal to Y, and BD is equal to K. And they want us to prove something about AB, that AB is equal to K tan of X times cos of Y minus root 3 sine of Y. Now that looks pretty complicated, but let's break it down and see what is it that they're actually looking for. So let's go back to our diagrams. This diagram is a bit simple in terms of there's only 2 triangles, actually 3 triangles, but probably 2 that we're going to work with. So we have this right angle triangle, ABC, which is right angled at B, but we only have one bit of information. We only have this angle X. That's all we have, which means as it stands, we cannot solve that triangle. So they're looking for AB, we're looking for AB, but we can't do anything in that triangle till we found something else. So there's a good chance we need to find BC first. Once we find BC, then to find AB is pretty easy because BC is the adjacent side and that's the opposite side, because then we could use tangent in that triangle. So we need to find BC first. BC belongs to this green triangle here. And so far we've got this angle, this side, we have the angle across it, okay? We have this angle here, and that's all we have. So we do have 3 things in that triangle, which means we probably can solve it, but we've got to just make sure that we use the correct rule. So obviously we've got 1 pair of matching angles inside, which means we're probably going to use the sine rule. But the problem with using the sine rule to find BC is we do not have currently the angle across it. So our first strategy to see if we can find the angle across it, and of course we can, because we know this angle is 150 and we know this angle is Y, so we can definitely write an expression for D. D will be 180 minus those 2 angles. So once we have that, we can probably find BC, and once we found BC, we can then find AB. So that's our strategy. Let's go and implement that. Okay, in triangle ABC, we said tan of X is equal to AB over BC. So rearranging that, AB is equal to BC times tan of X. Okay, and then we're now going to find our angles like we said. So D will equal to this angle here, will equal to 180 minus 150, and we have that y. So basically, angle D is going to equal to 180 minus 50, which will give us 30, 30 minus y. So now we know that this angle is 30 degrees minus y. Okay, so now we're going to use sine rule because we have that full pair and we want to find BC. Okay, so we're going to use the sine rule and we're going to begin with BC because that's what we've got to find. Okay, so we're going to have BC in the numerator. So BC and the sine across it, which is D, this angle here that we've just found, we're going to substitute it in just now. And the other full pair that we have is BD, this side here, and the angle across it. So BD over sine of 150. Okay, and then D was 30 minus y, and BD was K, so we substitute those two in. Now we're going to just make BC the subject of the formula. Okay, so BC the subject of the formula by just multiplying through by 30 minus y, so it becomes K sine 30 minus y over sine of 150. Now, can you see where the metric work comes in, where the compound angles come in? Because now we want to simplify this. But now we have sine of 30 minus y. We don't know what to do with it. We're a bit lost. So we're going to use, this reminds us of our compound formula of sine of alpha minus beta. So we're going to split that up. And we're going to split that up in a second. But while we're going to split that up, we also have to realize that this bottom angle here, so our first thing is we're going to split that up in the next step. But also this angle here is not an acute angle, so we're going to make it an acute angle. And remember, 150 is 180 minus 30 degrees. Okay? If you were not using the calculator, you could have just found the sine of, if you were using the calculator, you could have just found the sine of 150 at this point. If the question asks you not to use the calculator, then you'll have to proceed as we're going. So you'd make it an acute angle first. Okay, then we're going to use this formula to split the 30 minus y up. So sine of alpha minus beta, sine alpha cos beta, cos alpha sine beta. So let's do that. So in other words, it's going to be sine 30 minus y. So it'll be sine of 30 degrees cos of y times cos of 30 degrees sine of y. That's just substituting this into that formula there. Okay, now at this point, you can see we've got all sines of 30s, cos of 30s, and if you are allowed to use a calculator, you can go ahead and use a calculator for sine of 30. If the question says without a calculator, then you will have to use special angles. Okay, so that's the expression we had in the previous slide. Now remember, if you're looking for sine of 30, then either you can use your calculator, if they say you can use your calculator. If they say you're not allowed to use your calculator, and then you can use special angles to find it. And remember, here's our special angles triangle. So we're going to use these two triangles here on the side to solve it. So sine of 30 is opposite. Oh, sorry about that. Sine of 30 is opposite over hypotenuse. So it's going to be 1 over 2. Cos of 30 is adjacent of hypotenuse, so it's going to be root 3 over your hypotenuse, which is 2. We're using that triangle. And sine of 30, again, is going to be a half. So for the denominator, we've got a half again. Okay, now once we reach this, we've done all the trigonometry. Now there's just algebra to clean up. Okay, so you can see on top you've got 2 as your common denominator. So you're going to common denominator that as soon as you can. So remember, 2 is your common denominator. So in other words, on top you're going to end up with cos y over 2 minus root 3 sine y over 2. So this piece here came from your numerator. And remember, because we were dividing by a half, and we can divide by a half as long as we invert and multiply by 2 over 1. So we've kind of moved a bit faster through the algebra, but that should be easier. So let me just repeat that again. In the numerator here, we just found 2 as a common denominator. So we got cos of y minus root 3 sine of y as our numerator. And then this half, we inverted it and multiplied because the divide by half becomes times 2 over 1. Now we're just going to multiply all the numerators out and see what cancels. And if you notice already, you'll notice that this 2 and this 2 will cancel out with each other. And all we're left with is k times cos y minus root 3 sine y. So that's what we left for BC. So BC is equal to k cos y minus root 3 sine of y. Now remember, what were we trying to prove? We were trying to find AB. But remember, before we find AB, we needed to find this side. And that's what we found now. So we found an expression for BC, and we got to go plonk it back into that original equation we started off with. And the original equation we started off with was, sorry, that's just where we were. So we had cos, BC was k cos y minus 3 sine y. But remember, we started off with AB was equal to BC tan x when we just started that using this triangle, because we said tan of x was equal to opposite over adjacent. We did that already. Now I'm going to take this expression for BC and substitute it in here. And let's see what happens. We ended up with k times cos y minus root 3 sine 2 times tan of x. And if you look at what they asked us to prove, it's exactly the same thing, except that the tan of x is in front. So just rearranging this, I'm going to end up with k tan x. Let me just get rid of this. K tan x times cos of y minus root 3 sine of x. And that's exactly what they wanted us to, what they needed us to prove. So remember, when you're proving these 3D trigonometry problems, break them up into individual triangles, and then look at each triangle to see if you have enough information to solve that triangle. If you do, then you can work with it. If not, you may have to use an adjacent triangle to try and find values to help you solve the original triangle. Hi, welcome back. So just before the break, we were dealing with 3D trigonometry problems where we needed to use compound angles and double angle formulae to solve the problems. Let's continue with our last problem for the day. In the diagram, we have RA equals to the height of the vertical tower. T and Q are 2 points in the same horizontal plane as the foot A of the tower. From the point T, the angle of elevation to the top of the tower is 60 degrees. RTQ is theta, ATR is 60, and TQR is 60, and they've given us that TQ is equal to K meters. The first question says, show that TR is equal to root 3K over root 3 cos theta plus sine of theta. There's a second question that asks us to calculate something about RA. They want us to find, sorry about that, they want us to find RA here. So the first question we're going to find TR, and the second question we're going to find RA in terms of K and theta as we have it here. But before we look at trying to answer our questions, let's go and analyze our diagram. So what they've given us is they've given us essentially information in 2 triangles. So the first triangle they've given us information in is they've given us this right angle triangle here, RAT, and RAT has a right angle here, and it has angle 60 degrees, this angle here being 60 degrees. Okay, and the second triangle they've given us is this inclined triangle here. I'm going to use a different color. So this triangle TQA. Okay, so in the blue triangle, we only have one bit of information, which means we cannot solve it. But in this inclined triangle, we've got a 60-degree angle. We've got this theta here, okay, and we have this side belonging to the inclined angle. So remember, they want us to find TR. Okay, so we're going to use this inclined triangle to find TR. Okay, let's look at it again. So because we're using the inclined angle to find TR, remember the inclined triangle looks like this. So we've got theta here at T, okay, and we've got 60 degrees at this point, okay, and we have that this is equal to K, and we're trying to find TR. Okay, so we're going to be using sine rule because we don't have enough information to use cos rule. But remember, to find sine rule, we will need to find this angle first. So let's begin there. Okay, so we're going to find that angle, and that angle is going to equal to, let me just erase my markings here. Okay, so remember, to find that angle R1, we're going to have to use those two angles. So it's going to be theta minus theta and alpha were the other two angles in that triangle. So we had theta and 60 degrees, sorry, theta and 60 degrees in that triangle. Okay, so in other words, we're looking for this angle here. So that angle is now going to equal to 120 minus theta. So again, let me draw the triangle up here. So we got this angle as 120 minus theta. That's our R, okay? And then we've got T and we've got Q. And Q is 60 degrees, and this one here was theta, and QT was K. So now we're going to apply our sine rule to that triangle. And remember, we said we're going to use sine rule. And how are we going to use sine rule? Let's remind ourselves. We said we're going to say, because we're looking for TR, we're going to say TR over the angle across it. So it's sine of Q, that angle, will equal to TQ. Here's our full pair over sine of R1. Now we're just going to go and put in our values for that. So we're going to get TR, and the angle across from TR is 60 degrees. Okay, and then TQ is K, and we already worked out R1 to be 120 minus theta. Okay. Now we're just going to do some rearranging. We're going to multiply throughout by sine of 60. So the sine of 60 goes into the numerator there. Let's continue on the next slide. Okay, so we had K times sine of 60. Now remember, we want to show TR is equal to this expression here on the left, on the right. So we've got to continue with that. So that means we've got to expand this. And how do we expand this? We're going to expand this using our compound angle formula. So when we expand that using our compound angle formula, sine of alpha minus beta becomes sine of 120 minus theta becomes sine 120 cos theta minus cos 120 times the sine of theta. Okay, all right. At this point, if you were asked to use a calculator, you could have just gone straight to the answer from this step here. From this step here, you could have started just finding sine of 60, sine of 120, and cos of 20 on a calculator. If the question didn't ask you that, then you would have had to convert it to a special angle. So I'm going to include this step, but if it says without a calculator, you do not need to use this step. But I'm going to show you this because a lot of questions do, if you are asked to use special angles, then you're going to have to use this. So you're going to have to first make sine of 20 converted by reducing it in the second quadrant to 180 minus 60, so it becomes sine of 60. Similarly, cos of 120 will become, because it's a second quadrant angle, remember cos of 120 becomes cos of 180 minus 60, so it just becomes cos of 60, and because it's second quadrant, it becomes negative, hence we have negative cos of 60. Right, so now we're going to remember when you're multiplying out also, just don't forget that when you're multiplying out, you need to multiply those two negatives and they'll give you a positive. And so we're going to end up with K times sine of 60 over this, and sine of 60, if you look at your diagram, is going to equal to opposite over hypotenuse. So it's going to be root 3 over 2. Now if you had a calculator, you could have just done it with the calculator if you were allowed to use the calculator. We're going to use this angles to do it, so we don't need a calculator. So sine of 60 is root 3 over 2. Again, root 3 over 2. And cos of 60, so it's going to be adjacent over hypotenuse, so it's going to be equal to a half. So either you used your calculator or you use special angles to get this far. Let's go write a neater version of it. Okay, so that's where we were in the previous slide. K times root 3 over 2, root 3 over 2 times cos of theta plus half of theta, sine of theta. Now this looks similar, but there's some things kind of wrong, but obviously it's because we have, we need to find a common denominator in here. And the common denominator is 2, so let's start off there. So if you find the common denominator, we're going to get root 3 cos of theta all over 2. So we just added the numerators. Okay, and then we got k root 3 over 2, and because we're dividing by this, we're going to invert and multiply. So remember, when we invert and multiply, we're going to swap these two around. So it's going to become times 2, because remember we swapped it around, so it's going to be 2 over the numerator and the denominator are going to move around, so times 2 over root 3 cos theta plus sine of theta. Okay, and remember, what did they ask us to prove? They wanted us to prove that tk is equal to root 3k over, this is the question, remember? So we're almost there. The only thing we've got to do is now cancel off that. And when we cancel that off, we're left with 3k in the numerator, which is what they wanted us to prove. And the denominator, we have root 3 cos theta over sine of theta. So basically, we've now proved exactly what they needed us to prove. Okay, the next part of the question asked us to show that RA is equal to 3k over 2 times root of 3 cos theta plus sine of theta. So we're going back to our right-angled triangle TRA, which means we're talking about this angle here, this triangle here. Okay, and remember, we need to find, we said we're going to use sine of RTA. So sine of 60 is equal to, sine of 60 is equal to opposite over hypotenuse. So it's equal to AR over RT or TR. Okay, so RA will equal to TR times sine of theta. And remember that we found TR in the previous question, and we had TR is equal to this expression here. So we're just going to plonk in that whole expression for TR, which was root 3k over root 3 cos theta plus sine of theta times sine of 60. Now we're going to substitute for sine of 60, because we know from our special angle triangles, or if you were using a calculator, sine of 60 is root 3 over 2. So we're going to put that into the equation. And remember, we're multiplying those two numerators together. So root 3k times sine of 60 becomes root 3k times root 3 over 2. And when we're multiplying root 3 times root 3, we know that we must end up with just 3. Okay, so that means our expression can be simplified into 3k over 2. This 2 will go into the denominator, so 2 times root 3 cos theta plus sine of theta. Okay, that brings us to the end of this lesson on 3D trigonometry. Thank you for joining me. Bye.